So what does it mean that we need a new formulation? It means that if we are going to try and apply this method to the system of equations that we write from a web graph, even, I don't know, 50 million pages, we are not going to fare very well. We need something that is efficiently implementable, okay? And also we have to understand when we are able to solve this system, when we are not able, and in case, how do we fix this, okay? So these are all problems that Brin and Page eventually had to overcome. So, next slide is just what I was telling you before. They consider a column stochastic matrix, and they write this equation. It is the same equation that we wrote. The only difference is that what is called M here corresponds to the MT that I wrote, okay? So this matrix is column stochastic. If you take the entries of a column, they sum to 1. It's not row stochastic. But otherwise, it's the very same formulation, okay? Well, and the picture is perfectly equivalent to the one I gave. Just to be clear. Okay? So, why would all this observation help us? So why does a matrix formulation help us at all? Why? I try to give you a reason, okay? Let's consider all the cases for now. Let's consider all the cases in which this equation, or if you want, this equation admits a solution with the condition okay? Let's consider all the cases in which you can solve this. So there exists a solution. How can you compute it? Okay, for now we don't ask ourselves, when can I solve this work? When can I not solve it? Let's consider all the cases in which we can solve it. Okay? However they are defined. Can I find a more efficient way to solve this in practice? Exploiting linear algebra. So, look at this equation. Or if you want, this other equation in which here you have MT, M transpose. This M corresponds to our M transpose, always remember. What this equation telling us? Look at it. You have seen matrix algebra, right? You have heard of eigenvalues, eigenvectors, yeah? Did you hear of them? Yes. What does this look like? What is R? It's an eigenvector, right? I mean, if we are able to solve this equation, then R is an eigenvector. And what is the eigenvalue? How much is the eigenvalue? 1. That's interesting. Okay. How do I find the main eigenvector? Well, the main eigenvector. Let's see if it is the main eigenvector. So for a second, I mean for a few minutes actually, I'm just going to use the blackboard. Okay, blank. Okay. Now, have you ever heard the phrase power method? Power method. Never? It's actually one of the most used ways to find the main eigenvector of a matrix when your matrix is very large. Okay? Now, so, for now, let's do the following. And this is only for the sake of writing the equations. Let's write it like this. This is the equation we want to solve. The same as this. Okay? And now let's ask the following. Let us ask the following question. Call so that we remove the t. Okay? I just call this the transpose of A so that I remove the transpose. And then our problem becomes the following. This is the problem we want to solve. Of course, we have a further condition that the sum of the RJs has to be 1, but we keep that for later. And also, we would like them to be positive, yeah, not negative. We don't know what to do with negative entries. I mean, we don't know how to interpret them. How can I solve something like this in general? What can I try? How can I find the main eigenvector of a generic matrix? I mean generic, any matrix. What I can try to do is the following. Of course, I don't know the values of R in advance. I want to compute them. How can I try to proceed? I can start in the following way. I can start with an initial value, like this, R0 equal to some value, some vector x. For example, it could be the vector of 1s, any vector actually. Okay? And then I do the following. I iteratively solve this system. Actually, I do the following. The first time I will compute AX, yeah, and get R1. You see? The second time I will compute A times R1 and get R2, and so on. I start doing this iteratively. What is going to happen? You understand what I want to do? I don't say that you have to understand where this takes. For me, it's just important that you understand what I am doing. I do this. Let me write it down as an algorithm. When am I going to stop? We don't know yet. At some point we will stop. But this is what I'm doing, okay? Now my question is, what happens to this vector as t increases over time? Okay? Yeah. Or who knows? Actually, it depends on something which is, if you look at it, this will not reveal you anything. It depends on the spectrum of the matrix. It depends on the spectral structure of the matrix. Okay? But this is what I'm doing, and this is normally called the power method. You just take, why is it called power? Where is the power here? Let me show you. Am I right? Because R0 is equal to x, right? Equal to? Yeah? Aha. There is some trick here. Okay. You see this? Do you agree with this? This is the generic iteration. It is just the same. I only expanded it. Do you see this? That is the reason why this is called the power method. At step t plus 1, this vector is equal to the application of the matrix t times to the initial vector. Why is that important? It is very important, actually, and there is a trick. Only I need, is everyone okay with this up to this point? Now this is a matrix, okay? Let's say it's a real matrix. It's not an imaginary matrix. Let's say it will be a nice matrix in the end. It will behave nicely. Actually, remember that this matrix is not any matrix. This is a column stochastic matrix. And that's, yes?
Okay, I have some problem with exponential. You said r to the 2 is a to the 2x. So r to the t plus 1 should be a to the t plus 1x.
Okay, let's expand this.
No, I understood that it's the last one. It shouldn't be a
This
to
one.
the t plus 1.
This one?
Yes.
Okay. Oh, my mistake. So you wanted to say this?
Yes.
Ah, okay, yes, you're right. Yeah, I never pay a lot of attention to indices. When it's a plus minus 1, it's only, if it is wrong, it means that when you define the index, you forgot a 1. It's, sorry, it's normally these type of things I fix at a later stage. My bad, but so it's okay. Everybody's happy with this. Good. Why would this be important? Actually, it would not be important if we didn't make another observation and we said the following. So this is a matrix. It's a square matrix. It will admit a system of eigenvectors and eigenvalues, right? Yeah? From your first year, you took, there was some exam in, I think, geometry, algebra, and you, for example, learned about Jordan decomposition, all this stuff. No Jordan decomposition. Right? all the matrices we are interested in, fortunately, don't require Jordan decomposition. They are better behaved. For example, all the matrices we are interested in typically have a system of eigenvalues which are simple. So you can always diagonalize the matrix in some way. Sometimes, unless the matrix is symmetric, the base of the eigenvectors will not be orthogonal. But these matrices we are interested in, you can always diagonalize them. Okay? So why am I saying this? What is x? X is any vector, right? We said we fix x without following a particular policy. So we pick a vector x of our choice. For example, it could be the vector of ones, or sometimes, as is actually done in, let's say, PageRank, you pick the vectors so that its components sum to 1. For example, one initial choice may be x equal to, so this is the vector of entries, each one equal to 1 over n. Okay? This can be a choice, but this is not necessary. So, how can we write this further? Let's say that these are the eigenvectors of A, and also these are the corresponding eigenvalues. Okay, one thing I can anticipate to you is that when you have stochastic matrices, this is 1, and the eigenvectors and the eigenvalues are always real. Okay, there is a deep reason for this I'm not going to explain, but you have to believe me at this point. The eigenvalues of a stochastic matrix are always real. I'm not saying they're positive. I'm just saying they're real. And of course, likewise are the eigenvectors. Why am I saying this? Because since this is a system of eigenvectors, it is a base of R to the n, right? So every other vector can be expressed as a linear combination of these vectors. Do you agree? So I can write yes? Is it clear why I can do this? Because this is a base, not necessarily an orthogonal base. So these vectors in general are not orthogonal to each other. It's alpha are constants. It's a linear combination. I don't know what is the linear combination, but I know for sure that there are real coefficients such that every vector x can be expressed as a linear combination of the eigenvectors. Good. And this is another fact that we are going to need. Now, what is a to the t times x? Yes? Okay, just by definition. So someone, maybe in case you just missed what I said, how can you write this? The only reason why I can write this is that I know that the eigenvectors of the matrix are they are a base of R to the n, and so every other vector in this space can be expressed as a linear combination of the eigenvectors. these are the coefficients of the linear combination. Do I know these alphas? No, I don't know them. I mean, I only know that there are some alphas. But I don't need to compute them. Huh? I just know that they are there, so I write them down. I give them a name, and I write them down. Okay? That's all. The alphas are not what I'm really interested in. They also have a meaning, of course, but we don't care about the meaning. We just care that X can be expressed as a linear combination of the eigenvectors. And why is this useful? That's very useful, actually, because now, so a to the t, despite the power, is a linear operator, right? A to the t is a matrix. Yes, every matrix is a linear operator. So when you apply a linear operator to a sum, we have the sum of the application of the linear operator to every member of the sum. Yes? Now what can we write? Is it clear from here to here? So, what can we say about this? Let's. How much is this? No. I. Lambda I. Yes? And so on. You see that? Hey, it is very nice to deal with eigenvectors. Huh? Everything becomes easier. Look. So, when you compute the power method, actually what you're doing is you're computing the powers of a linear combination of the eigenvectors, nothing more. It is not important which vector you start from. What will change for a different choice of the vector is just its coefficients, but all the rest is equal. Now, why is this important? Okay. It's always important. Actually, this type of thing is always working. But in particular, for stochastic matrices, we know the following thing. We know the following thing. So if you consider the eigenvalues in modulus, the absolute value, then okay, this is generally what happens unless the matrix has a problem. We will come back to that, to those problems. You remember when I started with this, I said, let's consider matrices that behave well, so where we can always solve the system. If we can solve that system, then this is going to happen. Okay, you have one and only one eigenvalue, which is the first one, which is equal to 1. All the others in absolute value are strictly less than 1. Okay? Another way of saying this is that the spectral radius of this matrix is exactly, of stochastic matrix is exactly 1. And otherwise, all other eigenvalues are less than 1. So this is the only one that belongs to the spectral circle, it's called. Okay? I'm not proving this. Actually, proving these things is not completely straightforward. But there is a well-founded, well-assessed theory on this. It's called Perron-Frobenius theory of stochastic matrices. Actually, it's a bit more general than that. Okay? Are you okay with this? So why is this important? Actually, this is very, very important. So I'm canceling this, but you should keep this into account, because this is going to play a key role. Now, how can I write this again? So since I know that the first eigenvalue is 1, I can write it. Yeah? Okay. So, remember, now, look at this equation. Tell me, what is going to happen as t increases? This shrinks. Yeah? Okay. So what is, now remember, we wanted to solve this equation. We wanted to solve the equation, yeah? This equation we wanted to solve, right? But we know that the main eigenvalue of this matrix is 1. So this is R is actually the main eigenvector, right? You agree? So actually, okay, you see that? So when we apply the power method to this matrix, it's not important where we start from. We get actually the vector R, so the main eigenvector, just scaled by a constant. That is not so important, actually. Why is the constant not so important? Because we already know that there is another condition we want to satisfy, which is so whenever we get a vector like this, we rescale the vector so that the sum of the components is equal to 1, and we get R. And we get this vector. Okay? That's it. If you start from a different, if you start with a different initialization, your alpha 1 will change. But again, you can just rescale the result, and you get your vector. Is it clear? And there is another thing to know, that what the theory predicts of stochastic matrices is that the main eigenvector of such a stochastic matrix always non-negative. So it means that every entry is a non-negative number. Okay? Which is beautiful, because you can look at them as probabilities by suitable rescaling. Also, what it is telling you is that For the other eigenvectors, you cannot say this. They can have positive, negative components. But for the first one, no. It's always non-negative. That's a remarkable result. That shows us that sometimes nature is not so bad. I mean, she's nice to us. Okay? So, is this method feasible in practice? Well, we will see, yeah, actually it is feasible and it is applied in practice. In the end, you never compute the powers of a matrix, which is a very, very expensive operation. Normally what you do is exactly this algorithm. Every time you have a matrix vector multiplication, which is something much easier to do, okay? And you can scale this up in several ways up to very large matrices. I mean, in practice, matrices that describe the web, okay? And also there is a number of optimizations that I will show you. This is not yet the way in which you compute PageRank. It is actually what Brin and Page originally had in mind, but this stuff is not working in all cases. Sometimes very strange thing can happen. For example, you solve this system and you realize that your vector R looks like this. It's a 0 everywhere with the except of one vertex, for example. It's not nice to score web pages, right? You have one page that is scoring highest, and then you have all other pages scoring 0, okay? Or sometimes what you get is that you have a more general picture like this. You have a subset of the vertices that get a non-negative score, a positive score, and all the others get 0, which is also not very nice. Why is this happening? In order to understand why this is happening, again, you have to look at the problem. You have to exploit the stochasticity of this matrix to look at this computation as a stochastic process. Why? Because the stochastic process, in this case, is described by stochastic matrices, and as such, it is described by Markov chains. And we know a lot of properties of Markov chains. In particular, we are able to say when a Markov chain will give rise to something like this and when not. And so maybe we have a way of slightly modifying the Markov chain so that we never get something like this. Is it clear? Anything which is, yes?
Just one thing about eigenvalues.
About eigenvalues.
The fact that we state that they are, apart from the first, they are less than 1 in modulo is something that we can prove, or is just an assumption?
No. You can prove it. Okay. I have to be precise about this. It is not always true.
Okay.
But it will be true for all the Markov chains we are interested in. Okay. In general, it is not enough for the matrix to be stochastic, to be row stochastic to achieve this. Or at least, for example, you can have a stochastic matrices in which there is a row or a column, depends on how you look at it, which contains zeros, because, for example, you have no outgoing links. In that case, this may not be true. Other cases in which this may not be true is when you cannot go from one place. I mean, when there are what is called the spider traps. I will delve into the details of this. Eventually, we will get stochastic matrices that where this is always true. But in order for this to be true, you need some further assumptions, which are not very strong, actually. Okay? So, but before we can describe this fact, we have to look at the process in a different way. Okay, that's essentially what I was showing you. Now, can I cancel all this stuff? I mean, essentially, it's the same things that are said in the slides. I mean, in the book on massive datasets. I mean, that's the theory, essentially. Now,
why alpha times the eigenvectors is equal to alpha times r?
Yes. Okay, this was alpha 1. That was alpha 1, W1, right?
Okay.
Now, okay, one thing I should say is the following. When I write this equation, I'm assuming that alpha 1 refers to the largest eigenvalue. Okay, so lambda 1 will be the eigenvector associated to the largest eigenvalue. Okay? So, then I make a second remark. The second remark requires a number of facts which I have not proven. I am just stating them. And the facts are the following. If A is Coulomb stochastic, this equation corresponds to is the equation that defines the main eigenvector of A. Why? Because since the matrix is Coulomb stochastic, the main eigenvalue is 1. And it is the only eigenvalue, eigenvector with eigenvalue 1, unless the matrix has some problems, which I'm going to discuss later. We assume the matrix has not those problems. Since this equation defines the main eigenvector, it has to be this one.
Okay.
So W1 has to be R. Okay, that was the point. So this I have proven. This.
W1 is the only eigenvector. So
Sorry?
W1 is the only eigenvector. So
Yes, I didn't know this is in advance. I just have, this I have proven. I have shown that eventually you get this as t grows large. Then I need some further facts. And the facts that I'm using is that for stochastic matrices, we know that the largest eigenvalue is 1. That is the fact that I'm using. This fact we are not proving. We take it as a fact. But if this is true, then R has to be W. Okay? Do you see that? Okay. Now, okay, probabilistic interpretation. We have a stochastic matrix. Yeah? Let's go back to our nice and friendly row representation. So we have seen that we are trying to solve this. And we have seen the following, that to solve this, now I'm using this form, but it's the same as the transpose form. That to solve this, what I was doing was the following. Now you understand why I changed and switched to column representation. I don't like to write things like this. So this equation is exactly the same as the one we were writing before. I've just transposed, okay? It is the same. If I write this like this is the equation we had before. I'm just writing it in row form now. Now I hope you will understand why I'm writing it in this way. Because to give a probabilistic interpretation, this form is more suited, it's more intuitive. Now, this is a way to solve this. Okay? What I didn't show yet was that the power method we have seen converges fast. But if you remember, So how fast is this going to converge? How fast? The speed. So if lambda I is a constant, I don't know, for example, I'm just putting a number. Let's say 0.75, the absolute value. This is going down exponentially fast. You see, every term here is going exponentially fast. So how slow is this going to be? Well, this depends on how slow this is going to be. It depends on yeah? You see that? Hey, are you following me? No. So everyone has each and every of you has agreed that this is is shrinking, right? I mean, some of these are positive or negative, but their absolute value is less than 1. So these powers are going down at every step. How fast? How fast are they going down? How fast depends on how small these numbers are, right? The smaller the numbers, the faster this goes down. You see that? So what is the speed of convergence? Well, to know more or less which is the speed of convergence, I have to look at the largest of these values. The smaller the largest of this value, the faster it goes down. So it's an exponential decrease. Of course, in some, let's say, limit cases in which this is very close to 1, I mean, convergence can even be polynomial. But in all cases of practical interest, this is going to be a constant sufficiently smaller than 1. Even, let's say, 0.9 is enough. And the number of steps before this becomes something very small, smaller than any constant, any small constant epsilon you may be interested in, is logarithmic. In what? In something like 1 over epsilon. Okay, this is a part, this can be an exercise we can look at if you want. It's not a hard problem to solve actually, but this can be an exercise. What I just want to make you understand is that the number t that I need before this becomes as small as I like is normally logarithmic in 1 over as small as I like. Okay? Is it clear? I'm not proving this now. So I want to say that the number of iterations of the power method that you have to do is not 10,000. Very often it is 50 or 60. Okay? Not 10,000. When you have 50, 60, very often you have a very good approximation of this. In order to help the speed of convergence, the PageRank does another little trick that forces this value to be smaller than 1 constant, which is typically 0.85. Okay, so convergence of the PageRank algorithm very often is in the order of a few tens of iterations. Okay, we will discuss this a bit further. I don't expect you to understand all details for the moment, but what I expect you to understand is that from this equation it follows that this term is going down exponentially fast with respect to the maximum value, to this maximum value. I hope you get that. Yeah? Lambda I to the t. Yes? In absolute value, lambda I to the t is going down exponentially fast. Correct? All this stuff here, these are vector, these are a base of eigenvectors. Regardless, they normally are taken to be vectors that have unit norm, unit Euclidean norm, just by convention. So what is important is that the multiplying terms here are going down exponentially fast. And this is happening at a very high pace. We will make, I promise, if I don't, you remind me, because I don't need to prepare the lecture. I've seen this stuff non-countable number of times. So we can do, if I forget, at some point you can ask me and say, hey, you had promised you will show us how fast this goes down. Can you please show us how fast this goes down? And I will do. I will be happy to do this. Okay? But for the moment, trust me. So this goes down fast, and pretty soon what is left is essentially this term, with the degree of accuracy that you want. So, once this is settled, we can go back here, because this is equivalent to that. Okay? Now, what is the meaning of this process in probabilistic terms? To see what is the meaning of this process in probabilistic terms, let us assume that R0, which was x, is, for example, so a probability distribution, right? You see? This tells you with which probability you will begin, you will be at any given point at time 0. So we can call t time, number of rounds. So assume now that this is a row stochastic matrix, okay? Do you recognize this equation? So, look at me. Do you agree that this equation is equivalent to yeah? This is written component by component. So what is the meaning of this equation? Do you agree with this picture? Yeah? Is it clear? Yeah? Let's try to give, so, what is this? We can think of it as a random walker. So a person, assume that I have a graph. I have a graph with directed links. I am a random walker. I start in a given node with some probability. So think of it as a random surfer who's browsing the web. You begin with one page, right? You start at a page, then you follow a link and visit another page. Then again, follow another link and so on. At every point, at every step, you are in one page, right? And you are following the links. Now, the difference between you and this model is that in this model, you are choosing the links uniformly at random. You don't choose your links uniformly at random, right? In this model, you do. Okay? So, what this is actually a case of a very well-known process, stochastic process, which is called a random walk in a directed graph. How does it work? I begin at some given node with a given probability. In this example, I begin in any of the n nodes with the same probability. And then, at every step, I randomly move to another node in the networks based among the ones which I can reach from the node I'm currently in. Let's see if this makes sense. What is the probability that at time 1, in the first step, I am at node j? Let's see. It is equal to the probability that I am in any of the neighbors, incoming neighbors of this node, times the probability that I will go to the node, actually, right? So you see, at every point in time, so at time 0, I can be in this node, I can be in this node, or in any other node, but I cannot be in two nodes at the same time, right? Either one or the other. And this is actually the total probability that I will be in J in the first step. For example, if I am, in the first step I was at node I, what is the probability that I will be in node J in the next step? It is equal to the probability of following the link Ij, which is exactly Mij. You see that? If I was in node K, the probability of being in node J at step 1 is equal to the probability of crossing this link, which is Mkj. Of course, each of these events has to be weighted by the probability of being at the originating point. You see that? Okay, so what is the takeaway lesson from this? If I have the distribution, the probability distribution of this random walk of being in any of the possible nodes at step 0, the probability of being in any other node at step 1 is just described by this equation, right? You see that? So this is the component-wise equation, and this is the vector representation. You see that? Likewise, the probability distribution in 2 steps, how much is it? Well, if I know the probability distribution in 1 step, I just need to multiply. Yeah? In general, if I have the probability distribution of being in any of the points after t steps, in any of the vertices, sorry, after t steps, what is the probability distribution of being in any of the vertex in t plus 1 steps? Just a matrix multiplication. That's it. Okay? So, this is describing a random walk. So at every point t, at every time t, the vector rt is giving me the probability that I am in any specific vertex after t steps of the random walk. What is the probability of being at a particular node j? The j, component j of this vector. Okay? That's it. Why is this a Markov chain? Well, because the Markov chain because actually a random walk is a special case of a Markov chain. Markov chains are more general than random walks. So each random walk is described by a Markov chain, but to describe a Markov chain as a random walk, you, for example, cannot simply use unweighted graphs, okay? You need more general weighted graphs, possibly directed. Is this clear? Why did we need to look at this as a random walk or a Markov chain? Because we know a lot about Markov chains. For example, we know when the Markov chain is actually converging to a stationary distribution, which is what happens. You remember from who never heard of Markov chains before? Okay, we'll have some work to do. But for all the others, if you heard of Markov chains, you know that very often you are interested in the stationary distribution of a Markov chain. Well, the stationary distribution of a Markov chain is defined by an equation like this. What does stationary mean? That if you apply the stochastic matrix to the stationary distribution, you obtain the same distribution again, right? So is this always going to have a solution? Not always, we know. In particular, what you have learned is that there is always a solution if the Markov chain is called ergodic, which means I will explain next time. And the PageRank, the difference between this random walk and PageRank, the real PageRank random walk, is that it is obtained from this random walk, slightly modifying it so that the resulting Markov chain is ergodic. That's essentially PageRank. So this is almost PageRank. This is the initial PageRank of Brin and Page before they realized it was not working in many cases. Then they fixed it a little bit, teleporting and so, and then poof, ergodic Markov chain. And you always get a stationary distribution, which is called PageRank. Is it clear? Today was a tough lecture, I know. But if you want to understand the beauties of this stuff, we need to understand them a little bit. Okay? So, how much time do I have? I don't see anything. I'm running out of time, so I give you my 2 cents piece of advice for Easter vacations, which are going to be very long this year. So, my advice, you take a peek into Markov chains. You will find them both discussed in the textbook, in the massive datasets textbook, and there is a number of tutorials about Markov chains. You just need the basics, not much more. They are an example of Markov processes, okay? It's a very important class of stochastic processes that you find everywhere. They are really pervasive. So it's, actually, I am a bit disappointed that you, in the probability class, in your undergrad courses, you never really take a serious peek at Markov chains. They are really useful. They very often are scattered here and there in different courses that choose them, but they should be taken seriously in one undergrad course, maybe in the 3rd year. So go over this stuff, meditate on it a little bit, go over the things we saw, trying to reconstruct what we did. I think this is your exercise for Easter. Meanwhile, the big guy and I are going to give more information about forming groups, how the exam is conceived, and how we assign the projects. Now it's almost time that we can start to assign projects, because we have covered, yeah, I know, but before you assign project, no. I know it's time, but before you assign projects, you should have covered enough material that you can assign them. Now that we have finished, almost finished with classification, we can start assigning projects. Okay, so we will need a few days because we have to select a set of papers and so on. But we're going to do that. So please, check this stuff carefully so that when we start again, I'll take it from here. Okay? So in particular, try to understand why all the stuff we have seen from the beginning corresponds to a random walk, and in particular a Markov chain, and in general a Markov chain. Okay, try to really reconstruct the passages that take here to the interpretation as a Markov chain. Then you may want to understand why the power method works. Fine, that's a good exercise. It's not very hard, but let's say to understand this, you don't really need to understand why it converges. Okay, we know now that it converges in most cases, but you don't need to understand that to understand why the very same equations, flow equations that we saw at the beginning correspond to a random walk. To understand that, you just have to look at this representation as a graph on which a random walk is moving randomly from one step to the next. Okay?